Hello, and welcome to the Late Lab. Before settling in, take a moment to like the video and subscribe to the channel if quiet journeys into science sound like something worth returning to. It helps more curious minds find their way here. And while getting comfortable, it would be lovely to hear where in the world this video is being watched or listened to tonight. Perhaps it is late evening in a quiet apartment, early morning somewhere across the ocean, or a calm afternoon with sunlight coming through the window. Wherever it is, that place in the universe is built from the same tiny quantum rules we will be exploring together. For most of everyday life, reality appears reassuringly solid. Tables feel firm. Light fills a room. Objects sit exactly where they seem to be. The world appears stable and predictable, following rules that feel simple and familiar. But beneath that calm surface lies a deeper layer of nature that behaves in ways that can seem almost impossible. In that hidden layer, particles can behave like waves. Matter can exist in several possible states at once. Two particles separated by enormous distances can somehow remain connected in ways that seem to ignore space itself. This strange domain is known as quantum physics. It is not science fiction, and it is not speculation. It is one of the most carefully tested scientific frameworks ever developed. Every laser, every computer chip, every modern piece of electronics quietly depends on these rules of the microscopic world, yet the rules themselves remain wonderfully strange. In the quantum world, certainty gives way to probability. Instead of exact paths, there are clouds of possibility. Instead of solid particles moving like tiny billiard balls, there are wave-like patterns of energy that spread and interfere and only reveal a definite outcome when measured. For over a century, physicists have been slowly uncovering these rules. Beginning with Max Planck's discovery that energy comes in tiny packets, continuing through Albert Einstein's work on light particles, and expanding through the revolutionary ideas of Niels Bohr, Werner Heisenberg and Erwin Schrödinger, an entirely new picture of reality began to emerge. A picture where the universe, at its deepest level, behaves far differently from what human intuition might expect. And yet, this unusual behavior does not belong only to distant laboratories or complex equations. It quietly underlies everything. Every atom in the air, every photon of light entering the eye, every chemical bond that holds matter together is governed by these same quantum principles. The remarkable thing is that these ideas do not require rushing through complicated mathematics to appreciate them. When explained slowly and simply, the quantum world becomes less intimidating and far more fascinating. That is exactly what this journey is about. Over the next while, the strange rules of quantum physics will be explored step by step, beginning with the scientific puzzles that first forced physicists to question classical ideas about energy and light, then gradually moving through the discoveries that revealed the wave-like nature of matter, the role of probability in nature, and the curious connections between particles that seem to stretch across space. Along the way, some of the most famous ideas in modern physics will appear: superposition, entanglement, the wave function. Concepts that may sound mysterious at first but slowly begin to form a coherent and surprisingly elegant picture of how the microscopic universe behaves. The goal here is not to rush toward complexity. Instead, it is to allow each idea to unfold naturally, giving the mind time to settle into the strange logic of the quantum world. Because once these ideas begin to take shape, something rather remarkable becomes clear. The world is not just stranger than expected. It is stranger in ways that remain calm, subtle, and quietly beautiful. So wherever this video is being watched from tonight, take a moment to settle in. The universe around that location, from the smallest atoms in the air to the distant stars beyond the horizon, follows the same deep quantum rules. And those rules are about to begin revealing themselves. For most of everyday life, the universe appears reassuringly predictable. A cup placed on a table stays there. A thrown ball follows a graceful arc through the air before falling back toward the ground. Light fills a room in a steady glow, allowing objects to be seen clearly and reliably. The physical world seems to follow rules that feel solid, dependable, and easy to understand. For centuries, those rules were described with remarkable success by classical physics. Much of this framework was established by the English scientist Isaac Newton in the late 17th century. Newton's laws of motion explained how objects move and how forces act upon them. Combined with Newton's law of universal gravitation, they described everything from falling apples to the motion of the moon around Earth. These ideas proved extraordinarily powerful. Engineers used them to design bridges and buildings. Astronomers used them to calculate the paths of planets and comets with astonishing accuracy. For many generations, Newtonian physics seemed to provide a nearly complete description of how the universe worked, and for everyday objects, it still does. If a stone is dropped from a height, classical physics predicts its motion almost perfectly. If a train travels along a railway line, the same laws describe its speed, its acceleration, and the forces acting on its wheels. Even the movements of entire planets remain accurately described by Newton's principles under most circumstances. Yet there is a hidden assumption inside this comfortable picture of reality. Classical physics works best when describing objects that are large enough to see, touch, or measure directly. Apples, cannonballs, trains, and planets behave according to these rules. But nature does not stop at those scales. Beneath the visible world lies a vastly smaller realm, a universe of atoms, electrons, and tiny particles of light known as photons. At this microscopic level, matter behaves in ways that would have surprised even the most confident 19th century physicist. When scientists began carefully investigating this realm, at the end of the 19th century, something puzzling emerged. The familiar laws of classical physics began to fail. Light did not behave exactly as expected. Heat radiating from glowing objects produced patterns that theory could not explain. Electrons inside atoms did not orbit the nucleus in the neat planetary paths that classical mechanics would suggest. Instead, the deeper scientists looked, the stranger nature appeared to become. This scientific mystery began to unfold at the start of the 20th century. In the year 1900, a German physicist named Max Planck was studying how hot objects emit light. When a piece of metal is heated in a furnace, it begins to glow. At first the glow is dull red, then orange, then yellow, and eventually bright white as the temperature rises. Experiments had measured this behavior with great precision. Yet when physicists tried to predict the pattern mathematically using classical physics, the results became absurd. The equation suggested that extremely hot objects should emit an infinite amount of energy at certain wavelengths. Nature quite sensibly refused to cooperate. To resolve this contradiction, Planck made a bold and unexpected proposal. He suggested that energy was not emitted smoothly and continuously, as classical physics assumed. Instead, energy could only be released in tiny, discrete packets. These packets of energy became known as quanta. Planck himself initially treated the idea as a mathematical trick, something useful for calculations rather than a literal description of nature. But the idea soon proved far more profound than anyone expected. Only a few years later, another physicist began exploring an even stranger implication. In 1905, Albert Einstein studied a phenomenon known as the photoelectric effect. Experiments showed that when light shines onto certain metals, it can eject electrons from their surfaces. Classical physics predicted that brighter light should always produce stronger effects. Yet the experiments revealed something different. Only light above a specific frequency could knock electrons free, no matter how intense the light became. Einstein explained this puzzle by proposing that light itself behaves as tiny particles, each carrying a fixed packet of energy. These particles are now called photons. The idea was revolutionary. For centuries, light had been understood primarily as a wave spreading through space. Einstein's work suggested that light also behaves like a stream of particles. At this point, nature had begun revealing an unsettling pattern. Light could behave as both a wave and a particle. Soon, the mystery deepened even further. In the 1920s, the French physicist Louis de Broglie proposed that the reverse might also be true. If waves like light could behave as particles, perhaps particles such as electrons could behave like waves. At first, the idea sounded almost absurd. Electrons were thought to be tiny solid objects, like miniature billiard balls inside atoms. But experiments soon confirmed de Broglie's prediction. When beams of electrons passed through certain crystals, they produced interference patterns identical to those created by waves of light. Matter itself could behave like a wave. This discovery forced physicists to rethink the very nature of reality at small scales. Particles were no longer simply tiny objects following precise paths through space. Instead, they displayed a curious dual character, behaving sometimes like particles and sometimes like waves. Understanding this strange behavior required a new framework. During the 1920s, a generation of brilliant scientists began constructing that framework. Among them were Niels Bohr in Copenhagen, Werner Heisenberg in Germany, and Erwin Schrödinger in Austria. Their work laid the foundation for what is now known as quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales known to science. It provides a mathematical language capable of predicting how electrons move within atoms, how photons interact with matter, and how particles behave under extremely precise experimental conditions. Remarkably, its predictions have proven extraordinarily accurate. Modern technologies such as lasers, semiconductor electronics, and magnetic resonance imaging all depend directly on quantum principles. Yet even as quantum theory succeeded in explaining the microscopic world, it also revealed a universe that behaves in ways that challenge everyday intuition. Particles can exist in several possible states at once. Their exact position cannot always be known with certainty. Two particles can become connected in ways that seem to ignore distance entirely. These ideas can sound almost mystical when first encountered, but they arise directly from careful experiments and rigorous mathematics developed by generations of physicists. Quantum physics is therefore not merely a collection of strange ideas. It is one of the most successful scientific theories ever developed, repeatedly confirmed by observation and experiment. Understanding it does not require racing through complicated equations or advanced mathematics. When approached patiently and explained clearly, the central ideas begin to reveal an elegant structure underlying the microscopic world. The key is to begin with the moment when classical ideas first began to crack. Because the story of quantum physics truly begins when scientists realized that long-accepted assumptions about energy, light, and matter could no longer explain what experiments were revealing. That realization opened the door to an entirely new understanding of nature, one that would gradually uncover the quiet and surprising rules governing the smallest parts of the universe. By the end of the 19th century, many scientists believed that the great mysteries of physics had largely been solved. The universe appeared orderly, predictable, and increasingly well understood. The major laws governing motion, forces, electricity, and light had been discovered, and those laws seemed capable of explaining almost everything that could be observed. At the center of this confidence stood two towering achievements of physics. The first was the system of mechanics developed by Isaac Newton more than 2 centuries earlier. Newton's laws of motion described how objects move and how forces influence their movement. Combined with the law of universal gravitation, they provided a clear explanation for falling objects, orbiting planets, and the motion of machines. For everyday phenomena, Newton's framework worked with astonishing accuracy. The second great pillar was the theory of electromagnetism, developed by the Scottish physicist James Clerk Maxwell during the 1860s. Maxwell unified electricity and magnetism into a single elegant theory, and showed that light itself is an electromagnetic wave travelling through space. Maxwell's equations explained how electric and magnetic fields interact, and how electromagnetic waves move at the speed of light. With this discovery, light, radio waves, and magnetism were all revealed to be different expressions of the same underlying physical phenomenon. Together, Newtonian mechanics and Maxwell's electromagnetism formed a powerful intellectual structure. Many scientists believed these theories had revealed the fundamental workings of nature. A famous remark often attributed to physicists of the era suggested that only a few minor details remained to be clarified. Some even believed that physics had essentially reached its final form. Nature, as it turned out, had other plans. Hidden within a few subtle experimental results were clues that the classical understanding of the universe was incomplete. At first, these clues appeared small and technical, the kind of puzzles that might eventually be solved with minor adjustments to existing theories. Instead, they would eventually lead to one of the greatest revolutions in scientific history. One of the most puzzling problems involved the way hot objects emit light. When any object is heated, it begins to glow. A piece of iron placed in a furnace will gradually change color as its temperature rises. At lower temperatures it appears dull red. As the heat increases, the glow becomes orange, then yellow, and eventually bright white. This familiar effect had been studied carefully in laboratories during the 19th century. Physicists developed devices known as blackbody cavities to measure how heated objects emit radiation across different wavelengths of light. A blackbody is an idealized object that absorbs all incoming radiation and then emits energy purely as a result of its temperature. Though no perfect blackbody exists in nature, certain laboratory devices could approximate this behavior extremely well. When researchers measured the spectrum of light emitted by these heated cavities, they discovered a precise pattern. At each temperature, the emitted light peaked at a specific wavelength, and then declined at both shorter and longer wavelengths. The pattern was consistent and reproducible. Yet when physicists tried to calculate this behavior using classical physics, the results became deeply troubling. According to classical electromagnetism and statistical mechanics, the amount of energy emitted at shorter wavelengths should increase without limit. As wavelengths became smaller and smaller, the predicted radiation would rise toward infinity. This prediction was clearly absurd. If classical physics were correct, even a warm cup of tea would emit an enormous amount of ultraviolet radiation. The universe would be flooded with high-energy light from every warm object. Fortunately for both tea drinkers and the stability of matter, this does not happen. Experiments showed that radiation actually drops sharply at very short wavelengths. Instead of increasing endlessly, the intensity falls away rapidly. This contradiction between theory and observation became known as the ultraviolet catastrophe. The name sounds dramatic, but it reflects a very real scientific crisis. Classical physics, which had seemed so complete and reliable, was producing predictions that clearly disagreed with experimental evidence. Solving this puzzle required a new idea. That idea emerged from the work of the German physicist Max Planck. Planck was studying blackbody radiation while working in Berlin at the end of the 19th century. He was deeply familiar with both thermodynamics and electromagnetism, and he initially attempted to solve the problem using conventional physics. When those attempts failed, Planck tried a bold and unconventional approach. In the year 1900, he proposed that energy could only be emitted or absorbed in tiny discrete packets, rather than flowing smoothly and continuously. These packets of energy were called quanta. Instead of energy being divided infinitely into smaller and smaller amounts, Planck suggested that there exists a smallest possible unit of energy associated with a given frequency of radiation. In simple terms, energy behaved less like a flowing stream and more like individual drops. Planck introduced a constant of proportionality that determined the size of these energy packets. This quantity later became known as Planck's constant, one of the fundamental constants of nature. Using this assumption, Planck derived a formula that accurately matched the observed spectrum of blackbody, radiation. The mysterious ultraviolet catastrophe disappeared from the equations, replaced by predictions that aligned perfectly with experimental data. At first, Planck himself treated the idea cautiously. He viewed quantization as a mathematical tool that helped reproduce the correct results, rather than as a literal description of how nature behaved. Even so, the consequences of this proposal were profound. If energy truly comes in discrete packets, then one of the most basic assumptions of classical physics had been overturned. Continuous processes would no longer fully describe how energy interacts with matter. Planck presented his results to the German Physical Society in Berlin, where the work attracted considerable interest among physicists of the time. The University of Berlin became an important center for further research, and the idea of quantized energy slowly began to circulate through the scientific community. At first, the proposal appeared to solve only a narrow, technical problem related to heated objects. Yet the implications would soon extend much further. If energy is emitted in discrete packets, then light itself might also possess a granular structure. And if that were true, the very nature of light, which Maxwell had described as a continuous wave, might need to be reconsidered. That realization would soon inspire a young physicist named Albert Einstein to take Planck's idea in a bold new direction. The quiet mathematical trick that solved the ultraviolet catastrophe was about to transform the understanding of light, matter, and the fundamental structure of the universe itself. At the beginning of the 20th century, the strange idea proposed by Max Planck was still viewed by many physicists as a mathematical convenience rather than a statement about how nature truly behaves. The suggestion that energy comes in tiny packets solved the problem of blackbody radiation, but it was not yet clear whether those packets represented something physically real. Then a young physicist working in Switzerland began examining another puzzling phenomenon involving light and matter. In the year 1905, Albert Einstein published a paper explaining an effect that had been quietly troubling experimental physicists for several decades. The phenomenon was known as the photoelectric effect. The experiment itself was surprisingly simple. When light shines onto certain metals, electrons can be knocked loose from the metal surface. These freed electrons can then be detected as an electric current. The effect had been observed in laboratories throughout Europe, and it appeared to confirm that light carries energy capable of interacting with matter. At first glance, the behavior seemed straightforward. Brighter light should carry more energy, and therefore should eject electrons with greater intensity. But the experimental results told a different story. Researchers discovered that increasing the brightness of light did not always cause electrons to be released. Instead, what mattered most was the color of the light, or more precisely its frequency. Light below a certain frequency could shine on the metal indefinitely without ejecting any electrons at all. The surface would simply absorb the light and remain unchanged. However, once the light reached a particular threshold frequency, electrons began to appear almost instantly. Even a very faint beam could trigger the effect as long as the frequency was high enough. This behavior was deeply confusing within the framework of classical physics. According to Maxwell's theory of electromagnetic waves, the energy carried by light depends on its intensity, not its frequency. A brighter light wave should deliver more energy to the metal surface, eventually building up enough energy to release electrons. But that was not what experiments showed. Instead, the electrons seemed to respond only to the frequency of the light, not to its brightness. Even more surprising, when the frequency was high enough, the electrons were ejected immediately. There was no gradual accumulation of energy. It was as if each tiny interaction between light and matter occurred in a single indivisible event. Einstein realized that this behavior could be explained if Planck's quanta were not merely mathematical conveniences but actual physical entities. He proposed that light itself is made of discrete packets of energy. Each packet behaves like a tiny particle, carrying a specific amount of energy, determined by the frequency of the light. These packets of light are now known as photons. In Einstein's explanation, when light strikes a metal surface, individual photons collide with individual electrons. If the photon carries enough energy, it can transfer that energy to the electron in a single interaction, allowing the electron to escape the metal. If the photon's energy is too small, the electron remains bound inside the metal regardless of how many photons arrive. The brightness of the light simply determines how many photons arrive each second. The frequency determines the energy carried by each photon. Einstein expressed this relationship through a remarkably simple rule connecting energy and frequency. The energy carried by a single photon is determined by multiplying Planck's constant by the frequency of the light. In spoken form, the relationship can be expressed as energy equals Planck's constant multiplied by frequency. This relationship revealed that higher frequency light, such as ultraviolet radiation, carries more energy per photon than lower frequency light such as red light. As a result, ultraviolet photons can eject electrons from metal surfaces while red photons often cannot, regardless of how bright the red light becomes. The idea was both elegant and deeply unsettling. For more than a century, experiments had shown that light behaves like a wave. Maxwell's electromagnetic theory had successfully explained reflection, refraction, interference, and diffraction. Waves spreading through space appear to describe the behavior of light beautifully. Einstein's proposal suggested that light also behaves like a stream of particles. In other words, light possessed a dual nature. Sometimes it behaved as a wave, Sometimes it behaved as a collection of particles. At first, many physicists resisted this idea. Even Max Planck, whose own work had inspired the concept, initially hesitated to accept that light itself was quantized. Yet the experimental evidence continued to accumulate. Over the following years, researchers tested Einstein's explanation in increasingly precise experiments. One of the most important confirmations came from the American physicist Robert Millikan. Millikan spent nearly a decade carefully measuring the photoelectric effect using refined laboratory equipment. His goal was initially to test Einstein's hypothesis and perhaps disprove it. Instead, the experiments confirmed Einstein's predictions with extraordinary precision. Millikan's measurements showed that the energy of ejected electrons depended exactly on the frequency of the incoming light in the way Einstein had described. The relationship involving Planck's constant held true across a wide range of experiments. Despite his initial skepticism, Millikan eventually acknowledged that Einstein's explanation was correct. By the early decades of the 20th century, the idea that light is composed of photons had become widely accepted. Einstein later received the Nobel Prize in Physics for this work, recognizing the profound importance of the photoelectric effect in establishing quantum theory. The consequences of this discovery were far-reaching. If light can behave as both a wave and a particle, then the classical distinction between waves and objects begins to blur. The neat categories that once organized physical understanding were no longer sufficient. Nature appeared to operate according to deeper principles that did not always align with everyday intuition. The idea that energy is tied directly to frequency also became a cornerstone of modern quantum mechanics. Planck's constant and the quantization of energy now appeared across many areas of physics, governing interactions between radiation and matter at the smallest scales. Atoms emit light in discrete frequencies. Electrons absorb specific amounts of energy when moving between atomic states. Even the behavior of molecules and solid materials reflects this underlying quantum structure. The discovery that light consists of photons was therefore not an isolated curiosity. It marked the beginning of a new understanding of energy itself. But the story did not end there. Once scientists accepted that waves such as light could behave like particles, a remarkable question began to emerge. If waves can sometimes behave like particles, perhaps particles might also behave like waves. That possibility would soon lead physicists into one of the most surprising discoveries in the entire history of science. By the early 1920s, the picture of light had already changed dramatically. Experiments had shown that light behaves as both a wave and a particle. Waves spreading through space could also arrive in tiny packets of energy called photons. This dual nature of light was strange enough on its own. But a young French physicist soon wondered whether the symmetry might run deeper. His name was Louis de Broglie. De Broglie came from a family deeply connected to science. His older brother Maurice de Broglie was already an established physicist working with X-ray spectroscopy in Paris. Immersed in this scientific environment, Louis de Broglie began thinking about the strange discoveries surrounding light. If light, traditionally understood as a wave, could behave like a particle, perhaps the reverse might also be true. Perhaps particles could behave like waves. This was a daring idea. In everyday experience, particles and waves appear fundamentally different. A particle seems like a localized object occupying a definite position in space. A wave spreads out, oscillates, and interferes with other waves. Yet the discoveries of the early 20th century were already blurring these boundaries. De Broglie asked a simple but powerful question. If photons possess both wave and particle properties, why should this dual nature be limited only to light? In 1924, while completing his doctoral thesis at the University of Paris, de Broglie proposed that all matter possesses wave-like characteristics. According to his hypothesis, particles such as electrons are associated with waves whose properties depend on the particle's motion. Every moving particle would have an accompanying wavelength. This concept became known as the matter-wave hypothesis. The idea rested on a deep symmetry emerging within quantum physics. Light waves behaved as particles. De Broglie proposed that particles must therefore possess wave properties. Nature, it seemed, might not draw such a sharp distinction between objects and oscillations. De Broglie's proposal included a specific relationship between a particle's momentum and the wavelength of its associated wave. The relationship can be expressed in spoken form as wavelength equals Planck's constant divided by momentum. In this statement, momentum refers to the product of an object's mass and velocity. Planck's constant is the same fundamental quantity that appeared in the earlier work of Max Planck and Albert Einstein. The equation suggested that the wavelength associated with a particle becomes smaller as the particle's momentum increases. For large objects such as baseballs, trains, or planets, the resulting wavelength is extraordinarily tiny. The wave properties exist in principle, but they are so small that they cannot be observed with ordinary instruments. For very small particles such as electrons, however, the wavelength becomes measurable. This meant that under the right conditions, electrons might behave like waves capable of producing interference patterns. At the time, this prediction had not yet been confirmed experimentally. De Broglie's thesis therefore appeared somewhat speculative, yet the idea impressed some of the leading physicists of the day. Albert Einstein quickly recognized its elegance and supported the concept publicly. Within a few years, experiments would begin testing whether electrons truly possessed wave-like properties. Those tests arrived in a remarkable way. In the 1920s, two physicists working at Bell Telephone Laboratories in the United States were studying how electrons scatter from metal surfaces. Their names were Clinton Davisson and Lester Germer. Bell Laboratories, located in New Jersey, had become one of the most advanced industrial research centers in the world. Scientists there were investigating the behavior of electrons in metals in order to better understand electrical conduction and improve communication technology. During one series of experiments, Davisson and Germer directed a beam of electrons toward a nickel crystal. They measured how the electrons scattered after striking the crystal surface. The expectation, based on classical ideas about particles, was that the electrons would simply bounce off the atoms in the metal in predictable directions. But the results were not so simple. Instead of scattering randomly, the electrons formed distinct patterns of intensity that closely resembled the interference patterns produced when waves pass through a diffraction grating. The pattern looked strikingly similar to the diffraction patterns observed when X-rays interact with crystalline materials. In other words, the electrons appeared to behave like waves. This phenomenon became known as electron diffraction. The experiments demonstrated that electrons passing through a crystal lattice produce interference patterns characteristic of waves spreading through space. The crystal acted like a three-dimensional diffraction grating, bending the electron waves and creating alternating regions of high and low intensity. The measured wavelengths of the electrons matched precisely the values predicted by Louis de Broglie's equation. Almost simultaneously, similar confirmation came from experiments carried out by the British physicist George Paget Thomson at the University of Aberdeen. Thomson passed electron beams through thin metal films and observed diffraction rings, further confirming the wave nature of electrons. The evidence was now overwhelming. Particles of matter could behave like waves. This discovery marked one of the most profound turning points in the development of modern physics. The clear distinction between waves and particles had effectively collapsed. Instead of belonging to separate categories, matter and radiation appeared to share a deeper dual nature. Electrons could behave as localized particles when detected individually, yet exhibit wave-like interference when passing through narrow structures. Light could behave as a continuous wave spreading through space, yet also appear as discrete photons transferring energy in tiny packets. This strange behavior became known as wave-particle duality. Wave-particle duality is one of the defining features of quantum physics. It states that the fundamental entities of nature cannot be described solely as particles or solely as waves. Instead, they possess characteristics of both. Exactly how this dual behavior arises would soon become the central question facing theoretical physics. The discoveries of de Broglie, Davison, Germer, and Thomson revealed that the microscopic world operates according to principles very different from everyday intuition. Matter itself could form waves spreading across space, interfering and overlapping in ways that classical particles never could. Explaining these phenomena required a new theoretical framework capable of describing particles that behave like waves. Within only a few years, physicists including Werner Heisenberg and Erwin Schrödinger would begin constructing that framework. Their work would give rise to an entirely new language for describing nature at the smallest scales, a language known today as quantum mechanics. By the middle of the 1920s, physicists had gathered a collection of strange and intriguing discoveries. Light behaved as both waves and particles. Electrons could produce interference patterns like ripples spreading across water. Energy appeared to come in discrete packets rather than flowing smoothly and continuously. Yet despite these remarkable insights, there was still a problem. Scientists did not yet possess a complete theory capable of describing how these quantum phenomena actually worked. Individual discoveries existed, but the deeper rules governing the microscopic world had not yet been assembled into a coherent framework. The challenge facing physicists was clear. A new theory was needed, one that could explain the behavior of particles that sometimes behaved like waves, and waves that sometimes behaved like particles. Over the next few years, that theory began to take shape in a burst of intellectual creativity that transformed physics forever. Two scientists working independently would play central roles in building this new framework. Their approaches looked very different at first, yet both ultimately described the same underlying reality. One of them was the German physicist Werner Heisenberg. Heisenberg was a young researcher working in the lively scientific environment of Germany during the early 1920s. At the time, the University of Göttingen had become one of the leading centres for theoretical physics. Under the guidance of the mathematician David Hilbert and the physicist Max Born, Göttingen attracted brilliant young scientists eager to solve the mysteries of the quantum world. Heisenberg became deeply involved in the problem of describing atomic behavior. Physicists knew that electrons move within atoms and produce discrete spectral lines when atoms emit light. These spectral lines had been carefully measured in laboratories and provided clear clues about the internal structure of atoms. However, classical physics struggled to explain why electrons inside atoms produced only specific frequencies of light rather than a continuous spectrum. Heisenberg decided to approach the problem in an unusual way. Instead of attempting to describe the exact motion of electrons inside atoms, he focused only on quantities that could be directly observed in experiments. These included measurable properties such as the frequencies and intensities of spectral lines emitted by atoms. This shift in perspective proved revolutionary. In 1925, Heisenberg developed a mathematical method for calculating atomic behavior using arrays of numbers that describe transitions between energy states. The mathematics involved complex patterns of quantities interacting with one another in ways that differed significantly from traditional equations used in classical physics. This formulation became known as matrix mechanics. The name comes from the mathematical objects called matrices that Heisenberg used to describe quantum quantities. Although the calculations were challenging, the method successfully predicted the spectral properties of atoms. Shortly afterward, Max Born and Pascal Jordan at the University of Göttingen helped refine Heisenberg's theory, placing it on a firm mathematical foundation. Together, their work marked the first fully developed version of quantum mechanics. Around the same time, another physicist was approaching the quantum problem from a completely different direction. His name was Erwin Schrödinger. Schrödinger was an Austrian physicist working in Zurich when he encountered the ideas proposed by Louis de Broglie. De Broglie had suggested that particles possess wave-like properties, and Schrödinger became fascinated by the possibility of describing particles as waves spreading through space. Instead of using matrices and discrete transitions, Schrödinger sought a wave equation that could describe how these matter waves evolve over time. In 1926, he succeeded. Schrödinger developed a mathematical equation that describes how the wave associated with a quantum particle changes as the system evolves. The equation provided a way to calculate how an electron behaves inside an atom by treating the electron not as a tiny orbiting particle, but as a wave distributed through space. This idea led to a radically new picture of atomic structure. Rather than moving in precise circular orbits like planets around the Sun, electrons were now understood as forming patterns of probability distributed around the atomic nucleus. These patterns are known as atomic orbitals. Some orbitals resemble spherical clouds surrounding the nucleus. Others form complex shapes with lobes extending in different directions. These structures arise naturally from solutions to Schrödinger's equation. Schrödinger's formulation became known as wave mechanics. Although wave mechanics and matrix mechanics appeared very different at first, it soon became clear that they were mathematically equivalent. Both approaches describe the same underlying quantum behavior using different mathematical languages. The equation that Schrödinger developed remains one of the central tools of quantum physics. In spoken form, the relationship expressed by the equation can be summarized as the rate of change of a quantum wave equals the total energy acting on that wave multiplied by the wave itself. Although the full equation involves advanced mathematics, its conceptual meaning is remarkably elegant. It describes how the quantum state of a system evolves over time in response to the energies present within that system. Using this equation, physicists could now calculate the allowed energy levels of atoms, predict spectral lines with remarkable accuracy, and describe how electrons behave within molecules and solid materials. Quantum mechanics had arrived, but the theory raised profound questions about the nature of reality. If particles are described by waves spread across space, what exactly is the meaning of that wave? Does it represent a physical object, or does it describe something more abstract? Physicists began debating these questions intensely. One of the most influential attempts to interpret quantum mechanics emerged from discussions taking place in Copenhagen, Denmark. At the University of Copenhagen, the Danish physicist Niels Bohr had established an international research centre where many of the leading figures in quantum physics gathered to exchange ideas. Bohr, along with Werner Heisenberg and several colleagues, developed an interpretation that attempted to explain what the mathematical framework of quantum mechanics was actually telling scientists about nature. This perspective became known as the Copenhagen interpretation. According to the Copenhagen interpretation, the wave described by Schrödinger's equation does not represent a physical wave like a ripple in water. Instead, it represents a set of probabilities describing where a particle might be found when measured. Before a measurement takes place, the particle does not possess a single definite position. Instead, its behavior is described by a range of possible outcomes, each with a specific probability. Only when a measurement occurs does the system appear to settle into one particular result. This interpretation introduced a striking new idea into physics. At the most fundamental level, nature does not always provide precise predictions for individual events. Instead, quantum theory often predicts probabilities for different possible outcomes. This probabilistic view of reality differed sharply from classical physics, where knowing the position and motion of an object allowed its future behavior to be predicted with certainty. Quantum mechanics suggested that uncertainty and probability are woven into the fabric of nature itself. These ideas sparked lively debates among physicists. Some, including Albert Einstein, were uncomfortable with the notion that fundamental processes might be governed by probability rather than strict determinism. Others accepted the probabilistic interpretation as an unavoidable consequence of the experimental evidence. Regardless of interpretation, the mathematical success of quantum mechanics was undeniable. The theory explained atomic structure, chemical bonding, and the spectral lines emitted by elements. It provided the foundation for understanding semiconductors, lasers, and many modern technologies. The universities of Copenhagen and Göttingen became central hubs for this scientific revolution. Students and researchers travelled from across Europe and beyond to participate in the development of the new theory. Within only a few years, quantum mechanics had reshaped physics. Yet the theory also revealed a universe far stranger than the classical world imagined by Newton and Maxwell. Particles could exist in overlapping states. Their properties could not always be known with perfect precision. Measurement itself appeared to play a curious role in determining physical outcomes. A new vision of reality was beginning to emerge, one in which certainty gave way to probability, and familiar ideas about particles and waves merged into something far more subtle. As the new theory of quantum mechanics began to take shape during the 1920s, physicists gradually realized that the microscopic world does not behave according to the same intuitive rules that govern everyday experience. In classical physics, objects follow clear and predictable paths. If a ball is thrown across a field, its motion can be calculated precisely. Knowing its starting position, its speed, and the forces acting upon it allows its future location to be predicted at any moment. This approach reflects a principle known as determinism. Determinism assumes that the universe operates like an intricate clockwork mechanism. Every event follows inevitably from the conditions that came before it. If enough information is known, the future can in principle be calculated with exact precision. This view of nature dominated physics for centuries. Quantum mechanics introduced a different perspective. At the scale of atoms and subatomic particles, the theory does not describe particles travelling along well-defined paths. Instead, it provides probabilities for where a particle might be found when measured. This shift from certainty to probability represents one of the most profound conceptual changes in the history of science. At the centre of this new approach lies a mathematical object known as the wave function. The wave function was introduced through the work of Erwin Schrödinger, whose equation describes how quantum systems evolve over time. The wave function itself can be thought of as a mathematical description of the possible states available to a particle. However, the meaning of this wave function was not immediately obvious. Was it physical wave moving through space like a ripple across water, or was it something more abstract? A crucial insight came from the German physicist Max Born. In 1926, while studying the mathematics of quantum mechanics at the University of Göttingen, Born proposed an interpretation that would become central to modern quantum theory. According to Born, the wave function does not describe a physical wave of matter spreading through space. Instead, it represents a distribution of probabilities. In other words, the wave function tells scientists how likely it is to find a particle at different locations when a measurement is performed. Where the wave function is large, the probability of detecting the particle is high. Where the wave function becomes small, the probability decreases. Born expressed this idea by showing that the probability of finding a particle at a particular location is proportional to the square of the wave function's magnitude. In spoken form, this relationship can be described as probability equals the square of the wave function. Although the mathematics behind this statement can become complex, the concept itself is remarkably intuitive. Instead of imagining a particle moving along a precise trajectory, quantum mechanics describes a cloud of possible locations. When a measurement is made, the particle is detected at a specific point within that cloud. This idea becomes particularly clear when examining the structure of atoms. In the classical model proposed by Niels Bohr earlier in the 20th century, electrons were pictured as tiny particles, orbiting the nucleus along circular paths, somewhat like planets moving around the Sun. Quantum mechanics replaced this planetary model with something more subtle. According to Schrödinger's equation and Born's interpretation, electrons inside atoms are described by wave functions that spread throughout the surrounding space. These wave functions create regions where the probability of finding an electron is higher or lower. The result is often visualized as a probability cloud surrounding the atomic nucleus. These probability clouds form the structures known as atomic orbitals. Some orbitals appear roughly spherical. Others form shapes resembling lobes extending in several directions. The exact shapes depend on the energy level and quantum properties of the electron. These patterns are not physical clouds made of tiny particles. Instead, they represent regions where the electron is more or less likely to appear when observed. An electron might be detected anywhere within this region, though some locations are far more probable than others. This probabilistic description explains many features of atomic behavior. It accounts for the stability of atoms, the arrangement of electrons in different energy levels, and the chemical properties that arise from these structures. Yet it also introduces a surprising philosophical implication. In classical physics, the uncertainty about a particle's position arises only because measurements are incomplete. With sufficiently accurate instruments, it would in principle be possible to determine the particle's exact location and predict its motion perfectly. Quantum mechanics suggests something different. The uncertainty described by the wave function is not merely a limitation of measurement. It reflects a fundamental property of nature. Before observation occurs, the particle does not possess a single definite position in the classical sense. Instead, it exists in a state described by a range of possible outcomes. This interpretation challenged long-standing assumptions about determinism in physics. Albert Einstein, one of the founders of quantum theory, found this idea difficult to accept. He famously expressed his discomfort by remarking that he could not believe that nature plays dice with the universe. Many physicists shared Einstein's unease. The idea that fundamental processes might be governed by probability rather than strict cause and effect seemed deeply unsettling. Yet experiment after experiment confirmed the predictions of quantum mechanics. When electrons pass through narrow openings, they produce interference patterns characteristic of waves. When photons strike detectors, they appear as individual localized events, yet the distribution of those events follows the probability patterns predicted by the wave function. The statistical behavior predicted by quantum mechanics matched experimental observations with remarkable precision. Rather than eliminating uncertainty, the theory incorporated it directly into the mathematical structure describing nature. Despite its philosophical strangeness, this probabilistic framework proved extraordinarily successful. It allowed scientists to understand atomic structure, chemical bonding, and the behavior of materials with remarkable accuracy. Modern technologies such as semiconductors, lasers, and atomic clocks all rely on predictions derived from this probabilistic description of the microscopic world. In this sense, probability became not a weakness in scientific understanding, but a fundamental feature of the universe at small scales. The wave function provides the map of possible outcomes. Probability determines where a particle is likely to appear. But there remains an intriguing question that physicists continue to explore. If the wave function describes many possible outcomes, how does one particular outcome become reality when a measurement takes place? This question leads to one of the most fascinating aspects of quantum theory. The act of observation itself appears to play a surprisingly important role in determining what actually happens. The probabilistic nature of quantum mechanics raises an intriguing question. If the wave function describes many possible outcomes at once, how does a single definite result appear when a measurement takes place? This question lies at the center of what physicists call the measurement problem. Quantum theory provides an extraordinarily accurate mathematical framework for predicting the probabilities of different outcomes. When electrons pass through an experimental device, the theory predicts where they are most likely to appear. When atoms absorb or emit light, quantum mechanics predicts the precise frequencies involved. Yet the theory describes these outcomes only in terms of probabilities. Before a measurement occurs, the wave function contains a range of possible states. Each state represents a potential outcome that could be observed. Once a measurement is made, however, only one of those possibilities becomes reality. The transition from multiple possibilities to a single result is known as wave function collapse. This idea does not mean that the wave function physically explodes or vanishes. Instead, the mathematical description of the system suddenly changes. The spread of possible outcomes narrows to one specific state that matches the result observed in the experiment. In practical terms, this means that a quantum particle may be described by a wide probability distribution before measurement. But once the particle is detected, its position becomes definite. The puzzle lies in understanding what actually triggers this transition. In classical physics, observation simply reveals a property that already exists. If a thermometer is placed in a cup of tea, it measures the temperature that the tea already possesses. Quantum mechanics suggests something more subtle. Before measurement, certain properties may not exist in a definite form. Instead, the system exists in a range of possibilities. Measurement appears to play a role in determining which possibility becomes real. Physicists sometimes describe this by saying that quantum systems are not fully defined until they interact with a measuring device. This interaction forces the system into one of its possible states. Although the mathematics describing this process is well understood, the deeper meaning remains open to interpretation. Several scientists explored this question in creative and sometimes surprising ways. One of the most famous illustrations of the measurement problem came from the Austrian physicist Erwin Schrödinger. In 1935, Schrödinger proposed a thought experiment designed to highlight the strange implications of quantum theory when applied to everyday objects. The scenario imagines a sealed box containing a cat, a small radioactive atom, a detector, and a mechanism capable of releasing poison. If the radioactive atom decays, the detector triggers the poison and the cat does not survive. If the atom does not decay, the cat remains alive. Radioactive decay is governed by quantum probabilities. Before measurement, the atom exists in a superposition of decayed and not decayed states. If the entire system follows the rules of quantum mechanics, then the cat inside the box becomes linked to that quantum event. Until the box is opened and the system observed, the cat would appear to exist in a superposition of alive and not alive states. Schrödinger did not propose this scenario as a literal description of reality. Instead, he intended it as a demonstration of how puzzling the measurement problem becomes when quantum ideas are extended to larger objects. In practice, interactions with the environment quickly destroy such large-scale superpositions. Nonetheless, the thought experiment remains one of the most famous illustrations of quantum uncertainty. Other physicists examine the measurement problem from different perspectives. The Hungarian-American mathematician and physicist John von Neumann explored the role of measurement in his 1932 book on the mathematical foundations of quantum mechanics. Von Neumann argued that the measuring device itself must be treated as part of the quantum system. If that device is described using quantum mechanics, then its interaction with the system should also produce a superposition of outcomes. Following this reasoning leads to what is sometimes called the von Neumann chain. Each stage of measurement becomes entangled with the previous one. The measuring instrument, the recording device, and even the observer could in principle become part of the quantum description. The question then becomes where the chain ends. One of von Neumann's students, the Hungarian-American physicist Eugene Wigner, explored an even more speculative possibility. Wigner suggested that human consciousness might play a role in the collapse of the wave function. According to this idea, the act of conscious observation could be what ultimately resolves the quantum superposition into a single outcome. Most modern physicists do not consider consciousness to be necessary for measurement, yet the proposal illustrates how deeply the measurement problem challenges traditional assumptions about observation. Today, researchers typically describe measurement as a physical interaction between a quantum system and a larger environment. When a quantum particle interacts with measuring equipment, the system becomes entangled with the surrounding environment. This process leads to decoherence, in which the delicate quantum superpositions break down and the system behaves in a way that appears classical. Even so, debates about the interpretation of measurement continue. Different interpretations of quantum mechanics attempt to explain the process in different ways. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, emphasizes the role of measurement as the point where probabilities become physical outcomes. Other interpretations suggest that all possible outcomes may continue to exist simultaneously in separate branches of reality. Some physicists explore hidden variable theories that attempt to restore a more deterministic description of nature. Despite these philosophical differences, the practical predictions of quantum mechanics remain extraordinarily reliable. Every modern experiment involving atoms, photons, and electrons confirms the probabilistic framework introduced during the 1920s. The measurement problem therefore stands as a reminder that the quantum world operates according to principles very different from the everyday experience of macroscopic objects. Particles can exist in a spread of possibilities before observation. Their properties emerge only when interactions with measuring devices occur. This unusual feature leads naturally to another remarkable aspect of quantum behavior. If quantum systems can exist in several possible states before measurement, then those possibilities can coexist simultaneously within the same system. This phenomenon is known as superposition, and it represents one of the most distinctive and powerful ideas in all of quantum physics. In classical physics, a system is always in one definite state at any given moment. A coin resting on a table shows either heads or tails. A light switch is either on or off. A planet occupies one precise position along its orbit. The universe described by classical physics behaves with this kind of clarity. Objects possess specific properties, and those properties exist whether anyone measures them or not. Quantum mechanics tells a different story. At the smallest scales of nature, particles do not always exist in just one state. Instead, they can occupy several possible states simultaneously. This situation is known as quantum superposition. To understand this idea, it helps to think again about the wave function. The wave function describes all the possible outcomes available to a quantum system. When a particle exists in a superposition, its wave function includes several possibilities at once. An electron, for example, might have several possible positions around an atomic nucleus. Rather than choosing one specific location, the electron is described as existing in a blend of those possibilities until a measurement takes place. This does not mean that the electron rapidly jumps between positions like a tiny restless insect. Instead, the mathematical description of the electron includes multiple possibilities that coexist in a single quantum state. When a measurement is finally performed, one outcome becomes definite. The superposition resolves into a single result. Before that moment, the particle exists in a state that contains several possibilities at once. Although this idea may seem abstract, experiments demonstrate it clearly. One of the most famous demonstrations involves a device known as the double-slit experiment. This experiment has been repeated many times using electrons, photons, atoms, and even large molecules. The setup is surprisingly simple. A beam of particles is directed toward a barrier containing two narrow openings. Beyond the barrier lies a screen capable of detecting where each particle arrives. If particles behave strictly like tiny objects, they would pass through one slit or the other, producing two clusters on the screen behind the barrier. Instead, something remarkable occurs. When many particles are sent through the slits, the pattern that appears on the screen forms a series of bright and dark bands. This pattern is known as an interference pattern, and it is characteristic of waves overlapping and interacting. The same type of pattern appears when ripples on water pass through two openings and spread outward. The implication is extraordinary. Each particle behaves as though it passes through both slits simultaneously, creating an interference pattern with itself. In quantum terms, the particle exists in a superposition of paths. It does not travel through only the left slit or only the right slit. Instead, its wave function includes both possibilities at once. Only when the particle is detected on the screen does one definite outcome appear. Experiments with electrons first revealed this behavior during the 20th century, but later research extended the phenomenon to many other systems. Photons of light show the same interference effects. even atoms and small molecules have produced interference patterns when carefully controlled in laboratory experiments. At the Massachusetts Institute of Technology, researchers have conducted precise studies of quantum interference using beams of atoms cooled to extremely low temperatures. Similar experiments at the Max Planck Institute for Quantum Optics in Germany have explored interference effects with individual photons and ultra-cold atomic gases. These studies confirm that superposition is not a rare or exotic occurrence. It is a fundamental property of quantum systems. The scale at which superposition operates can be quite astonishing. In certain experiments, individual particles are separated into different paths that extend several meters apart before recombining to produce interference. The particle behaves as though it occupies both paths simultaneously until detection occurs. For everyday objects, this behavior is impossible to observe because interactions with the surrounding environment quickly destroy the delicate quantum state. This process is known as decoherence. But at microscopic scales, where systems can be carefully isolated, superposition remains one of the defining features of the quantum world. The concept also plays a crucial role in modern quantum technology. One of the most promising applications appears in the field of quantum computing. Traditional computers process information using bits, which exist in one of two states commonly described as 0 or 1. Quantum computers operate differently. Their basic units of information, known as quantum bits or qubits, can exist in superpositions of multiple states simultaneously. Instead of representing a single value at any moment, a qubit can encode several possibilities at once within its quantum state. This property allows quantum computers to explore many potential solutions to a problem in parallel, offering the possibility of solving certain calculations far more efficiently than classical computers. Research groups at institutions including MIT, IBM Quantum, and the Max Planck Institute are actively investigating how to control superposition within physical systems such as superconducting circuits, trapped ions, and ultra-cold atoms. Although practical large-scale quantum computers remain under development, the fundamental role of superposition in these technologies is already clear, yet superposition alone does not capture the full strangeness of the quantum world. In some situations, quantum particles can become linked together in a way that makes their properties inseparable, even when the particles are separated by large distances. This phenomenon is known as quantum entanglement, and it introduces an even deeper layer of mystery into the nature of the universe. Among the many unusual ideas that appear within quantum physics, few have provoked as much fascination as quantum entanglement. The concept describes a situation in which two or more particles become linked together in such a way that their properties cannot be described independently. Instead, the particles share a single combined quantum state. At first glance, this may sound like a poetic metaphor rather than a scientific statement. Yet entanglement arises naturally from the mathematical structure of quantum mechanics and has been confirmed repeatedly through carefully controlled experiments. To understand the basic idea, imagine two particles created in a process that binds their properties together. One simple example involves a pair of photons emitted from a single atomic interaction. The photons may emerge with their polarizations connected in such a way that measuring one immediately determines the polarization of the other. Individually, each photon appears to exist in a superposition of possible states. Neither one possesses a definite polarization until a measurement takes place. However, the pair as a whole possesses a well-defined relationship. When one photon is measured and its polarization becomes known, the state of the second photon becomes determined at that same moment, even if the two photons are separated by great distances. This peculiar linkage is what physicists call entanglement. In classical physics, such behavior would seem impossible. If two objects are separated in space, one would normally expect that any influence traveling between them must move through space over time. Quantum entanglement appears to defy this expectation. The correlations between entangled particles emerge instantly when measurements occur, regardless of the distance between them. This strange implication troubled several of the founders of quantum theory. Among them was Albert Einstein. Although Einstein helped launch the quantum revolution through his work on the photoelectric effect, he remained uneasy about certain aspects of the theory. In particular, he questioned whether quantum mechanics provided a complete description of reality. In 1935, Einstein collaborated with the physicists Boris Podolsky and Nathan Rosen to analyze this problem in detail. Their work produced a thought experiment now known as the Einstein-Podolsky-Rosen paradox. The argument considered a pair of particles created in such a way that certain properties of the pair are precisely linked. For example, two particles might be emitted with equal and opposite momenta. Measuring the momentum of one particle would immediately reveal the momentum of the other. Einstein, Podolsky, and Rosen reasoned that if measuring one particle instantly determines the state of another distant particle, then either information is traveling faster than light, or the particles must possess hidden properties already determined before measurement. Einstein found the first possibility deeply troubling because it appeared to conflict with the principle of relativity, which states that no influence can travel faster than the speed of light. For this reason, he suspected that quantum mechanics might be incomplete. Perhaps there existed hidden variables underlying the theory, determining the outcomes of measurements in ways not captured by the standard equations. Einstein famously described entanglement as spooky action at a distance, a phrase that has remained closely associated with the concept ever since. For many years, this debate remained largely philosophical. Physicists could discuss the implications of entanglement, but designing experiments capable of resolving the issue seemed extremely difficult. That situation changed in the 1960s through the work of the Northern Irish physicist John Bell. Bell developed a mathematical framework capable of distinguishing between the predictions of quantum mechanics and those of hypothetical hidden variable theories. His result became known as Bell's theorem. Bell showed that if hidden variables governed the behavior of entangled particles, certain statistical relationships would always hold between measurements performed on the particles. Quantum mechanics, however, predicted that these relationships could sometimes be violated. This insight allowed the question to be tested experimentally. If experiments produced results that violated Bell's inequality, then hidden variable explanations of the Einstein-Podolsky-Rosen type could not fully account for the behavior of entangled systems. Testing Bell's theorem required extremely precise measurements of particles whose properties were correlated in subtle ways. One of the most influential experimental tests occurred in the early 1980s. The French physicist Alain Aspect and his colleagues at the University of Paris conducted a series of experiments using pairs of entangled photons. In these experiments, photons produced from a common source travelled in opposite directions toward detectors placed several meters apart. The detectors measured the polarization of each photon using rapidly changing measurement settings. The results revealed correlations between the photons that violated Bell's inequality exactly as quantum mechanics predicted. In other words, the experimental evidence supported the quantum description of entanglement rather than hidden variable explanations. Since Aspect's work, many increasingly sophisticated experiments have been performed around the world. These studies have tested entanglement across larger distances and with greater precision. Researchers have entangled photons separated by kilometers through optical fibers and even through free space between mountain tops. In some experiments, entangled particles have been transmitted between ground stations and satellites orbiting Earth. The results consistently confirm the predictions of quantum mechanics. Entanglement is not merely a theoretical curiosity. It is a real and measurable feature of the quantum world. Modern research institutions continue to explore the phenomenon in detail. At CERN, the European Organization for Nuclear Research near Geneva, physicists investigate entanglement in systems involving high-energy particles and complex quantum fields. In the United States, the National Institute of Standards and Technology conducts precision experiments using trapped ions and ultra-cold atoms to study entangled quantum systems. These studies help refine measurement techniques and deepen understanding of quantum correlations. Entanglement has also become a central resource in emerging quantum technologies. In quantum communication systems, entangled photons can be used to generate cryptographic keys that reveal any attempt at interception. This technique, known as quantum key distribution, provides a new form of secure communication based on the laws of physics rather than computational complexity. In quantum computing, entanglement allows multiple qubits to share information in ways that classical bits cannot replicate. When several qubits become entangled, the system can explore many possible computational states simultaneously, greatly expanding its potential processing power. Researchers at institutions such as the Massachusetts Institute of Technology, the University of Oxford, and the Max Planck Institute for Quantum Optics are actively developing methods to generate and control entangled states with increasing precision. Despite these technological advances, entanglement still carries a sense of quiet mystery. Two particles created together can remain linked across distances that may span laboratories, cities, or even satellites in orbit. Measuring one particle reveals information about the other instantly, regardless of how far apart they have traveled. Importantly, this connection does not allow information to travel faster than light. The correlations appear only when the results of both measurements are later compared through ordinary communication. Even so, the existence of such deep connections between distant systems challenges classical ideas about separateness and locality. Quantum entanglement reveals that the microscopic world is not composed merely of isolated objects interacting across empty space. Instead, particles can share relationships that bind their properties together in subtle and far-reaching ways. These relationships, once viewed as puzzling theoretical curiosities, have now become essential tools for advancing modern technology. And as researchers continue to explore their possibilities, entanglement is gradually moving from the realm of philosophical debate into the practical foundations of the quantum technologies shaping the future. At the heart of every atom lies a tiny central nucleus surrounded by a region where electrons move according to the rules of quantum mechanics. This structure forms the foundation of chemistry, materials science, and much of modern technology. Yet the way electrons behave inside atoms is very different from the tidy planetary systems that early scientists once imagined. To appreciate this difference, it helps to begin with the first successful attempt to explain atomic structure using quantum ideas. This step was taken by the Danish physicist Niels Bohr in the year 1913. Bohr was working at the University of Copenhagen, which would later become one of the great centers of early quantum research. His goal was to understand the structure of the hydrogen atom, the simplest atom in nature, consisting of a single proton in the nucleus and a single electron surrounding it. Earlier models had pictured electrons orbiting the nucleus much like planets circling the Sun. According to classical electromagnetism, however, such orbits should not be stable. An electron moving in a circular path is constantly accelerating, and accelerating electric charges should radiate energy. If classical physics were correct, the electron in a hydrogen atom would continuously lose energy and spiral inward toward the nucleus. The atom would collapse in a fraction of a second. Clearly, this does not happen. Atoms remain stable, and hydrogen atoms throughout the universe behave in remarkably consistent ways. They also emit light at very specific frequencies when excited, producing a set of spectral lines known as the hydrogen emission spectrum. Bohr proposed a bold solution. He suggested that electrons are allowed to occupy only certain discrete orbits around the nucleus. These orbits correspond to specific energy levels. While the electron remains in one of these permitted orbits, it does not radiate energy. Light is emitted only when the electron jumps from a higher energy orbit to a lower one. This idea explained the observed spectral lines of hydrogen with impressive accuracy. Each spectral line corresponded to a transition between two allowed energy levels. Bohr's model was an important step forward, yet it still relied on the picture of electrons moving along defined circular paths. As quantum mechanics developed during the 1920s, this picture would evolve into something more subtle and more accurate. The full quantum description of atoms emerged through the work of scientists such as Erwin Schrödinger, Werner Heisenberg, and Max Born. In this framework, electrons are not treated as tiny particles traveling along fixed trajectories. Instead, their behavior is described by the wave function. The wave function represents the possible locations where an electron might be found when measured. Rather than orbiting like planets, electrons exist as probability distributions surrounding the nucleus. These probability distributions are known as orbitals. An orbital describes a region of space where the electron is most likely to appear. The shapes of these orbitals arise naturally from solutions to Schrödinger's wave equation. Some orbitals form simple spherical regions centered around the nucleus. These correspond to the lowest energy states of the atom. Other orbitals form more complex structures with lobes extending in different directions. These shapes can resemble pairs of balloons, cloverleaf patterns, or elongated clouds stretching along specific axes. Each orbital represents a unique solution to the quantum equations governing the electron's motion. Importantly, these structures are not rigid objects. They represent patterns of probability. When an electron is detected within an atom, it appears as a localized particle, but the likelihood of where it appears is determined by the orbital's probability distribution. This quantum description explains why electrons do not collapse into the nucleus. The allowed energy states of the atom restrict the electron's behavior, preventing it from occupying arbitrary positions or energies. Another key principle governing atomic structure was introduced by the Austrian physicist Wolfgang Pauli. In 1925, Pauli proposed what is now known as the Pauli exclusion principle. This rule states that no two electrons within the same atom can occupy identical quantum states simultaneously. Each electron is defined by a set of quantum numbers that describe properties such as energy level, angular momentum, and magnetic orientation. The Pauli exclusion principle ensures that each electron must differ in at least one of these quantum numbers. This rule has profound consequences for the structure of matter, because electrons cannot crowd into the same quantum state. They fill atomic orbitals in an orderly sequence. Lower energy orbitals fill first, followed by higher energy ones. This arrangement determines the structure of the periodic table of elements. For example, the hydrogen atom contains only one electron, which occupies the lowest energy orbital. Helium contains 2 electrons that share this orbital, but differ in a property known as spin. The next element, lithium, must place its 3rd electron in a higher energy orbital because the lowest one is already filled. As atoms grow larger and contain more electrons, the filling of orbitals becomes increasingly complex. Yet the overall pattern remains governed by the quantum rules discovered during the early 20th century. This quantum structure of atoms lies at the foundation of chemistry. Chemical bonding occurs when electrons interact between neighboring atoms. The shapes and energies of atomic orbitals determine how atoms share or exchange electrons to form molecules. For instance, the structure of a water molecule arises from the arrangement of oxygen and hydrogen orbitals combining to create stable bonds. The geometry of carbon orbitals allows carbon atoms to form long chains and complex molecules, making organic chemistry and life itself possible. In materials science, the same quantum principles explain why different substances conduct electricity, reflect light, or exhibit magnetic behavior. Metals conduct electricity because their electrons occupy energy bands that allow them to move freely through the material. Insulators hold their electrons tightly within filled energy bands. Semiconductors such as silicon occupy a delicate middle ground that allows their electrical properties to be controlled. Modern electronic devices, from computers to smartphones, depend entirely on this quantum behavior of electrons within solid materials. Even everyday objects quietly rely on these principles. The color of a gemstone arises from quantum transitions between electron energy levels. The strength of a chemical bond reflects the arrangement of electron orbitals between atoms. What began as a puzzling attempt to understand atomic spectra eventually revealed the deeper structure of matter itself. Quantum mechanics transformed the picture of atoms from miniature solar systems into dynamic probability landscapes shaped by wave functions and quantum rules. These principles apply not only within individual atoms, but across the entire microscopic world. From the behavior of molecules to the properties of crystals and the interactions between subatomic particles, the same quantum laws continue to govern the smallest scales of nature. And as scientists explore further into that microscopic realm, those laws reveal an even richer tapestry of phenomena waiting to be understood. These same quantum rules that shape atoms do not stop at the boundaries of chemistry. When scientists began exploring deeper into the structure of matter, they discovered that the quantum description of particles required an even more powerful framework. The behavior of electrons inside atoms can be explained with the tools of quantum mechanics developed during the 1920s, yet particles can also move at speeds approaching the speed of light. When that happens, the effects described by Albert Einstein's theory of special relativity become important. Relativity describes how space and time behave when objects move extremely fast. Quantum mechanics describes how matter and energy behave at extremely small scales. During the early 20th century, physicists realized that a complete theory of nature would need to combine both ideas. The framework that eventually emerged is known as quantum field theory. Quantum field theory represents one of the most profound changes in how scientists think about particles. In earlier pictures of the microscopic world, particles were often imagined as tiny objects moving through empty space, somewhat like miniature billiard balls traveling along invisible tracks. Quantum field theory replaces that picture with something far more subtle. According to this theory, the fundamental ingredients of nature are not particles but fields. A field is a physical quantity that exists throughout space. The temperature of the air in a room forms a field, because it has a value at every point in space. The gravitational field surrounding Earth extends outward in all directions and determines how objects fall toward the planet. In quantum field theory, every type of particle is associated with its own underlying field that fills the entire universe. Electrons are associated with the electron field. Photons are associated with the electromagnetic field. Quarks, neutrinos, and many other particles each correspond to their own fields. Within this framework, what we call a particle is actually a small excitation of the corresponding field. An analogy can help make this idea clearer. Imagine a calm surface of water stretching across a lake. If a small disturbance occurs, ripples spread across the surface. Those ripples are not separate objects independent of the water. They are patterns of motion within the water itself. Quantum field theory describes particles in a similar way. A particle is like a ripple traveling through an underlying field. The field exists everywhere, and the particle appears when the field becomes locally excited. This picture may seem abstract, yet it has proven extremely powerful in explaining the behavior of subatomic particles. One of the first major breakthroughs in this direction came from the work of the British physicist Paul Dirac. In 1928, Dirac developed an equation that combined quantum mechanics with the principles of special relativity to describe the behavior of electrons moving at high speeds. The Dirac equation successfully predicted the electron's properties, including its intrinsic angular momentum known as spin. Even more remarkably, Dirac's equation implied the existence of particles identical to electrons but carrying opposite electric charge. These particles became known as positrons, the antimatter counterparts of electrons. A few years later, the American physicist Carl Anderson detected positrons in cosmic ray experiments, confirming Dirac's prediction and providing one of the earliest experimental successes of relativistic quantum theory. As quantum field theory developed further, physicists gained new tools for calculating the interactions between particles. One of the most influential figures in this development was the American physicist Richard Feynman. Working during the 1940s, Feynman introduced a visual method for representing particle interactions using diagrams that track how particles exchange energy and momentum. These illustrations, known as Feynman diagrams, allow physicists to calculate complex interactions by breaking them into simpler steps involving the exchange of force-carrying particles. The electromagnetic force, for example, can be understood as the exchange of photons between charged particles. When two electrons repel each other, they do so by exchanging photons within the electromagnetic field. Feynman's methods provided a powerful way to perform calculations within quantum field theory, helping transform the subject into a practical tool for predicting experimental outcomes. Within this framework, even empty space reveals unexpected behavior. In classical physics, the vacuum is simply empty space containing nothing at all. Quantum field theory paints a different picture. Because fields exist everywhere, even a region devoid of particles still contains the underlying fields themselves. These fields cannot remain perfectly still due to the uncertainty principle discovered by Werner Heisenberg. As a result, tiny fluctuations occur continuously within the vacuum. These fluctuations can briefly produce pairs of particles and antiparticles that appear and disappear within extremely short times. These short-lived entities are known as virtual particles. Virtual particles cannot be directly observed in the same way as ordinary particles, but their effects can influence measurable physical phenomena. For example, the interaction between virtual particles slightly alters the energy levels of electrons inside atoms. This effect, known as the Lamb shift, was measured with great precision during experiments in the 1940s and 1950s. Another example occurs in the Casimir effect. When two metal plates are placed extremely close together in a vacuum, the quantum fluctuations of the fields between them create a tiny force that pushes the plates toward each other. These subtle effects provide evidence that the vacuum is not truly empty. Instead, it is a dynamic environment filled with fluctuating quantum fields. Modern particle physics experiments probe these ideas with remarkable precision. One of the most important research centers for studying quantum field theory in action is CERN, the European Organization for Nuclear Research, located near Geneva in Switzerland. At CERN, scientists operate powerful particle accelerators capable of propelling protons and other particles to speeds extremely close to the speed of light. These particles are then collided with enormous energies, briefly recreating conditions similar to those that existed in the early universe. The debris from these collisions reveals new particles and interactions predicted by quantum field theory. Experiments at CERN have confirmed many aspects of the theory, including the existence of previously unknown particles and the detailed behavior of fundamental forces. Through these investigations, physicists have developed an increasingly unified description of the microscopic world. Quantum field theory provides the mathematical language used to describe the fundamental particles and forces of nature. It reveals that the universe is built not from isolated objects moving through empty space, but from interacting fields whose excitations appear to us as particles. This framework forms the foundation for the modern theory of particle physics. That theory, known as the Standard Model, brings together the known fundamental particles and the forces that govern their interactions into a single coherent structure describing the smallest building blocks of the universe. As the picture of quantum fields and particle interactions grew clearer during the 20th century, physicists gradually assembled a framework capable of describing nearly all known subatomic phenomena. This framework became known as the Standard Model of particle physics. The Standard Model represents one of the most successful scientific theories ever developed. It provides a detailed description of the fundamental particles that make up matter and the forces that govern how those particles interact. At its heart, the Standard Model describes a universe built from a small collection of basic ingredients. These ingredients combine in countless ways to produce everything from atoms and molecules to stars and galaxies. The particles described by the Standard Model fall into two broad categories. The first category contains the particles that make up matter itself. These are known as fermions. The second category contains particles responsible for carrying forces between matter particles. These are known as bosons. Among the matter particles, two important families appear again and again in nature. These are quarks and leptons. Quarks are the building blocks of protons and neutrons. A proton, for example, is composed of two up quarks and one down quark bound together by the strong nuclear force. A neutron contains two down quarks and one up quark. These quarks are never observed in isolation under normal conditions. Instead, they remain confined inside composite particles, known as hadrons. This confinement arises from the strong nuclear force, which becomes stronger as quarks attempt to separate. The strong force itself is carried by particles known as gluons. These gluons act as the messengers of the strong interaction, constantly exchanged between quarks and binding them tightly together. Leptons form the second major family of matter particles. The most familiar lepton is the electron, which orbits atomic nuclei and plays a central role in chemistry and electricity. Electrons belong to a broader set of leptons that includes the muon, the tau particle, and 3 types of neutrinos. Neutrinos are especially elusive particles that interact only very weakly with matter. Trillions of them pass through the human body every second without leaving any noticeable trace. Together, the quarks and leptons form the basic building blocks from which all known matter is constructed. The Standard Model also describes several fundamental forces that govern how these particles interact. The electromagnetic force acts between electrically charged particles and is carried by photons, the particles of light. This force governs phenomena ranging from the structure of atoms to the behavior of electric currents. The strong nuclear force holds quarks together inside protons and neutrons and binds atomic nuclei together. As mentioned earlier, this interaction is carried by gluons. A third interaction, known as the weak nuclear force, is responsible for certain types of radioactive decay. The weak force plays a crucial role in processes such as nuclear fusion inside stars. It is carried by particles known as the W boson and the Z boson. Each of these interactions is described within the mathematical framework of quantum field theory. The fields associated with particles and forces interact according to precise rules, encoded within the Standard Model. Although the theory may appear complex, its predictions have been tested with extraordinary accuracy. Research institutions around the world have contributed to verifying the Standard Model through countless experiments. One of the most important centers for this work is CERN, located near Geneva in Switzerland. At CERN, the Large Hadron Collider accelerates beams of protons to speeds extremely close to the speed of light, before colliding them head-on. These collisions produce showers of particles that briefly recreate conditions similar to those present in the early universe. Detectors surrounding the collision points record the properties of the particles produced in these events. Another major research facility is Fermilab, the Fermi National Accelerator Laboratory, located near Chicago in the United States. Fermilab has conducted decades of experiments studying high-energy particle interactions, including important measurements of quarks and neutrinos. Together, facilities like CERN and Fermilab have tested the Standard Model with remarkable precision, yet one key piece of the puzzle remained missing for many years. According to the equations of the Standard Model, certain particles should acquire mass through interactions with a field that permeates all of space. This field is known as the Higgs field. The existence of the Higgs field was proposed during the 1960s by several physicists, including Peter Higgs, François Englert, and Robert Brute. Their work suggested that particles gain mass by interacting with this invisible field as they move through space. The particle associated with this field is called the Higgs boson. For decades, the Higgs boson remained hypothetical, because producing it required extremely high-energy particle collisions. That changed in the year 2012. Using the Large Hadron Collider at CERN, 2 major experimental collaborations known as ATLAS and CMS independently reported evidence for a new particle consistent with the Higgs boson. The discovery confirmed a crucial element of the Standard Model and represented one of the most important achievements in modern particle physics. Peter Higgs and François Englert were later awarded the Nobel Prize in Physics for their contributions to the theoretical prediction of the Higgs mechanism. Despite these successes, the Standard Model is not the final word on the fundamental laws of nature. The theory explains an enormous range of experimental results, yet several major mysteries remain beyond its reach. For example, the Standard Model does not include a description of gravity. The gravitational force is described separately by Albert Einstein's theory of general relativity, and physicists continue searching for a unified framework that can incorporate both quantum mechanics and gravity. The theory also does not explain the nature of dark matter, the invisible substance believed to make up most of the matter in the universe. Astronomical observations show that galaxies and galaxy clusters behave as though they contain far more mass than can be accounted for by known particles. In addition, the Standard Model does not fully explain why the universe contains far more matter than antimatter, even though both should have been created in equal amounts during the early moments after the Big Bang. These unanswered questions remind physicists that the Standard Model, while extraordinarily successful, is still incomplete. Understanding what lies beyond it remains one of the great challenges of modern science. Solving those mysteries may require new theories that extend the principles of quantum physics into deeper layers of reality. The Standard Model of particle physics provides an extraordinarily successful description of the microscopic world. It explains the behavior of fundamental particles, the forces that govern them, and the structure of matter down to extremely small scales. Yet one major force of nature remains outside this framework. That force is gravity. Gravity was described in a revolutionary way by Albert Einstein in the year 1915 through his theory of general relativity. In this theory, gravity is not treated as a conventional force. Instead, it emerges from the curvature of space and time caused by mass and energy. A useful way to picture this idea is to imagine space and time forming a flexible fabric. Massive objects such as stars and planets bend that fabric around them. Other objects move along the curved paths created by this distortion. This elegant description explains phenomena that classical Newtonian gravity cannot account for, including the bending of light around massive objects and the precise motion of planets near the Sun. General relativity has passed every experimental test placed before it. Observations of gravitational waves detected by the Laser Interferometer. Gravitational Wave Observatory confirmed predictions made by Einstein more than a century earlier. The motion of stars around the supermassive black hole at the center of the Milky Way also matches the theory's predictions with remarkable accuracy. Yet despite its success, general relativity operates in a very different conceptual world from quantum mechanics. Quantum theory describes particles, probabilities, and discrete packets of energy. General relativity describes smooth curves in the geometry of space and time. When physicists attempt to combine the two frameworks into a single theory, difficulties quickly arise. In quantum mechanics, physical quantities often fluctuate due to the uncertainty principle. Energy, position, and other properties cannot all be specified with perfect precision. These fluctuations are small at everyday scales, but they become significant when dealing with extremely tiny distances. General relativity, on the other hand, treats space and time as smooth and continuous. The equations describing space-time curvature assume a well-defined geometry. When quantum fluctuations are introduced into this geometry, the calculations become unstable. The mathematics produces infinities that cannot be easily removed. As a result, the two theories resist straightforward unification. This conflict between quantum mechanics and general relativity is one of the central problems in modern theoretical physics. Physicists refer to the search for a theory that successfully combines these ideas as the quest for quantum gravity. A complete theory of quantum gravity would describe how space-time behaves at extremely small distances where quantum effects become important. These distances are unimaginably tiny, roughly on the order of the Planck scale, where gravitational interactions and quantum fluctuations may become equally significant. Although no final theory has yet been confirmed, several promising ideas have emerged. One of the most widely studied approaches is string theory. String theory proposes that the fundamental entities of nature are not point-like particles, but tiny vibrating strings. Each possible vibration of these strings corresponds to a different particle. In this picture, electrons, quarks, and photons are simply different vibrational patterns of the same underlying objects. One remarkable feature of string theory is that it naturally includes a particle that behaves like the quantum carrier of gravity. This particle is known as the graviton. If confirmed, the existence of gravitons would allow gravity to be described within the same quantum framework as the other fundamental forces. String theory also suggests that spacetime may contain additional spatial dimensions beyond the three familiar dimensions of length, width, and height. These extra dimensions would be extremely small and tightly curled, making them difficult to detect experimentally. Another approach to quantum gravity takes a different path. This idea is known as loop quantum gravity. Loop quantum gravity does not attempt to replace particles with strings. Instead, it focuses directly on the quantum structure of spacetime itself. According to this theory, space may not be perfectly continuous. Instead, it could be composed of tiny discrete units woven together in a network known as a spin network. In this picture, spacetime resembles a finely textured fabric made of fundamental loops. Distances and areas would arise from the structure of this network rather than existing as infinitely divisible quantities. Loop quantum gravity attempts to apply the principles of quantum mechanics directly to the geometry described by general relativity. Both string theory and loop quantum gravity remain active areas of research. Physicists around the world continue exploring these ideas in the hope of uncovering a deeper understanding of the universe. Several major research institutions play important roles in this effort. The Perimeter Institute for Theoretical Physics in Waterloo, Canada, has become one of the leading centres for research in quantum gravity and related fields. Scientists there investigate fundamental questions about space-time, black holes, and the quantum structure of the universe. Another influential institution is the Institute for Advanced Study in Princeton, where Albert Einstein himself worked during the later years of his life. The Institute continues to host leading theoretical physicists studying the intersection of gravity, quantum mechanics, and cosmology. Understanding quantum gravity may prove essential for explaining some of the most extreme environments in the universe. Black holes provide one such example. Inside a black hole, gravity becomes so strong that space and time are warped to extraordinary degrees. Near the center of a black hole, known as the singularity, the curvature of space-time becomes immense. At these scales, the effects of quantum mechanics should also become significant. A complete description of what happens inside a black hole likely requires a theory that unites both quantum physics and general relativity. Another situation where quantum gravity may play a crucial role is the earliest moment of the universe. According to modern cosmology, the universe began in an extremely hot and dense state, roughly 13.8 billion years ago. During the earliest fractions of a second, the density and temperature were so extreme that quantum effects and gravitational curvature would have been deeply intertwined. Understanding those conditions may reveal new insights into how space, time, and matter first emerged. Although the search for quantum gravity continues, the progress made so far highlights how profoundly quantum physics has reshaped our understanding of the universe. Even before the deepest mysteries are solved, quantum ideas have already produced powerful technologies that influence everyday life in surprising ways. Those technologies provide a glimpse of how insights from the quantum world can move beyond theoretical physics and begin transforming the tools used throughout modern society. For much of the early 20th century, quantum physics appeared to belong entirely to the realm of abstract theory. It was a strange mathematical description of atoms, electrons, and photons, useful mainly for scientists trying to understand the microscopic structure of nature. Yet over time, those abstract ideas quietly became the foundation for many of the technologies that define modern life. Today, quantum physics operates behind the scenes in devices used every single day. It rarely announces its presence. Most people unlock a smartphone, turn on a computer, or visit a hospital without realizing that the behavior of electrons inside these machines follows the rules of quantum mechanics. In many ways, the modern technological world is built upon quantum principles. One of the most important examples appears in semiconductors. Semiconductors are materials whose electrical properties fall somewhere between those of conductors, such as copper, and insulators such as glass. Silicon is one of the most widely used semiconductor materials. The reason silicon behaves this way lies in the quantum structure of electrons inside the material. In solid materials, electrons do not occupy isolated atomic orbitals as they do in single atoms. Instead, they are allowed energies spread into ranges known as energy bands. These bands arise from the quantum interactions between vast numbers of atoms packed closely together in a crystal lattice. The key concept is the separation between two bands known as the valence band and the conduction band. Electrons normally occupy the valence band. However, if enough energy is provided, some electrons can move into the conduction band, where they're free to travel through the material and carry electric current. The size of the gap between these two bands determines whether a material behaves as a conductor, an insulator, or a semiconductor. In semiconductors, the energy gap is small enough that electrons can be encouraged to move between these bands under carefully controlled conditions. This property allows engineers to design devices known as transistors. A transistor acts as a tiny electronic switch that can control the flow of electrical signals. By arranging billions of these switches together on a small silicon chip, engineers can build complex circuits capable of performing calculations, storing information, and processing data. Modern microprocessors contain tens of billions of transistors, each operating according to quantum rules governing the behavior of electrons inside semiconductor materials. The development of transistor technology was strongly influenced by work carried out at Bell Laboratories in the United States during the mid-20th century. Scientists such as John Bardeen, Walter Brattain, and William Shockley played central roles in developing the first working transistor in the late 1940s. Their discovery transformed electronics and laid the foundation for the computer revolution. Another remarkable technology based on quantum physics is the laser. The word laser stands for light amplification by stimulated emission of radiation. Although the name may sound complicated, the underlying idea arises directly from quantum mechanics. The principle of stimulated emission was first described by Albert Einstein in 1917. Einstein showed that atoms could emit light in a coordinated way when they were stimulated by incoming photons of the correct energy. In a laser, atoms are excited into higher energy states. When they return to lower energy states, they release photons that are identical in energy, direction, and phase. This process produces an extremely focused beam of light with remarkable precision. Lasers now appear in an astonishing range of applications. They're used in fiber optic communication systems that carry information across continents through thin glass cables. They perform delicate surgical procedures in hospitals. They scan barcodes in supermarkets and measure distances in industrial equipment. Even the tiny optical sensor inside a computer mouse relies on laser technology to track motion across a surface. Another technology deeply connected to quantum physics appears in modern medical imaging. Magnetic resonance imaging, often known as MRI, allows doctors to produce detailed images of the inside of the human body without the need for surgery. MRI scanners operate using strong magnetic fields and the quantum behavior of atomic nuclei. The technique relies on the fact that certain atomic nuclei possess a property known as spin. When placed inside a magnetic field, these nuclei behave like tiny magnets that can align with or against the field. By applying carefully tuned radio waves, scientists can temporarily alter the orientation of these nuclear spins. As the nuclei return to their original alignment, they emit signals that can be detected and converted into detailed images of tissues and organs. MRI technology has become an indispensable tool in modern medicine, allowing doctors to diagnose injuries and illnesses with remarkable accuracy. Beyond these large and visible technologies, quantum mechanics also shapes many smaller aspects of everyday life. The colors of pigments and dyes arise from quantum transitions within molecules. The efficiency of solar panels depends on the quantum behavior of electrons inside semiconductor materials. Even the stability of ordinary matter results from quantum principles governing the arrangement of electrons within atoms. Without the Pauli exclusion principle discovered by Wolfgang Pauli, electrons would not organize themselves into the layered structures that give atoms their chemical properties. Chemistry itself depends on this arrangement. The periodic table reflects patterns in the quantum structure of atoms. In this sense, quantum physics quietly governs much of the physical world surrounding us. It determines how materials behave, how light interacts with matter, and how energy flows through the microscopic structures of technology. Although these ideas were once considered purely theoretical, they now influence industries worth trillions of dollars. Research institutions continue to explore new quantum-based technologies. Universities, national laboratories, and industrial research groups are investigating ways to harness quantum behavior even more directly. These efforts include attempts to build devices that operate using individual atoms, photons, and other quantum systems. One emerging area of research focuses on sensors capable of detecting extremely small changes in gravity, magnetic fields, or time itself. Another area involves communication systems that use quantum properties to create highly secure methods of transmitting information. Yet perhaps the most ambitious direction involves building entirely new types of computers based on quantum principles. These devices, known as quantum computers, promise to perform certain calculations in ways that differ fundamentally from traditional machines. Their development may represent the next major technological transformation, emerging from the strange and fascinating rules of quantum physics. The technologies already shaped by quantum physics are impressive, yet scientists have begun exploring an even more ambitious idea. Instead of simply using quantum effects inside materials, what if computation itself could be built directly from quantum rules? This question led to the development of a new field known as quantum computing. Traditional computers operate using bits. A bit is the most basic unit of digital information. Each bit can exist in one of two states, typically represented as 0 or 1. Every calculation performed by a classical computer ultimately involves manipulating long sequences of these binary digits. Quantum computers approach information in a different way. The fundamental unit of quantum information is known as the quantum bit or qubit. A qubit behaves according to the principles of quantum mechanics. Unlike a classical bit, which must be either 0 or 1, A qubit can exist in a combination of both states simultaneously. This property arises from the quantum phenomenon known as superposition. Superposition allows a quantum system to occupy multiple possible states at the same time until it is measured. In the context of quantum computing, a qubit can represent 0, 1, or a mixture of both possibilities. When several qubits are combined together, the number of possible states grows extremely rapidly. For example, 2 classical bits can represent 4 possible combinations. However, a pair of qubits can simultaneously explore multiple combinations through superposition. As the number of qubits increases, the number of possible states expands dramatically. This property creates the potential for a fundamentally new style of computation. Another key ingredient in quantum computing is entanglement. Entanglement is the quantum phenomenon in which 2 or more particles become linked so that the state of one particle cannot be described independently of the others. When qubits become entangled, their properties are correlated even when separated by distance. This connection allows quantum systems to perform coordinated operations that have no direct equivalent in classical computing. By carefully controlling superposition and entanglement, quantum algorithms can explore many possible solutions to a problem simultaneously. In certain cases, this allows quantum computers to solve particular types of problems much more efficiently than classical machines. One famous example comes from a mathematical method known as Shor's algorithm. Shor's algorithm was developed by the mathematician Peter Shor in the year 1994. The algorithm demonstrates that a sufficiently powerful quantum computer could factor very large numbers dramatically faster than classical computers. Factoring large numbers forms the foundation of many modern encryption systems used to secure online communication. The possibility that quantum computers might break these encryption methods has become an important topic of research in both computer science and cybersecurity. Another promising application involves searching through large data sets. A quantum method known as Grover's algorithm, developed by Love Grover in the 1990s, shows that certain types of searches can be accelerated using quantum computation. Beyond mathematics and cryptography, quantum computers may prove useful in simulating complex physical systems. Many chemical reactions and material properties depend on the quantum behavior of electrons interacting with each other. Classical computers often struggle to model these interactions accurately because the calculations become extremely complex as the number of particles increases. Quantum computers, however, operate according to the same quantum principles that govern these systems. This makes them potentially well suited for simulating molecules, chemical reactions, and advanced materials. Such simulations could help scientists design new pharmaceuticals, more efficient catalysts, and improved energy storage technologies. Because of these possibilities, research in quantum computing has expanded rapidly. Several major technology companies and research institutions have launched ambitious programs aimed at building working quantum computers. IBM has developed a series of experimental quantum processors and provides remote access to these machines through cloud-based platforms. Researchers around the world use these systems to test quantum algorithms and explore new approaches to quantum computation. Google Quantum AI has also made significant progress in this field. In 2019, researchers at Google announced that their experimental quantum processor had performed a specific calculation faster than the most powerful classical supercomputers available at the time. This milestone was described as an early demonstration of what researchers call quantum advantage. Universities are also deeply involved in quantum computing research. The University of Oxford hosts one of the leading academic programs focused on building quantum processors based on trapped ions. In these systems, individual charged atoms are held in place using electromagnetic fields and manipulated with carefully controlled laser beams. Other laboratories explore alternative technologies, including superconducting circuits, photonic qubits based on individual particles of light, and quantum systems built from defects inside crystals. Despite this progress, constructing a practical quantum computer remains extremely challenging. Quantum systems are extraordinarily sensitive to disturbances from their environment. Even tiny vibrations, stray electromagnetic fields, or slight temperature fluctuations can disrupt the delicate quantum states needed for computation. This problem is known as decoherence. Decoherence causes qubits to lose their quantum properties and behave like ordinary classical systems. Preventing this loss of coherence requires sophisticated experimental setups, often involving extremely low temperatures only a fraction of a degree above absolute zero. Another challenge involves correcting errors that occur during quantum calculations. Classical computers handle errors by storing multiple copies of information and checking for inconsistencies. Quantum information cannot be copied in the same way because of a principle known as the no-cloning theorem. To address this difficulty, scientists are developing methods of quantum error correction that distribute information across groups of qubits. These methods allow errors to be detected and corrected without directly copying the quantum state. Although practical, large-scale quantum computers have not yet been built, progress continues steadily. Each year, experimental devices grow slightly more stable and contain more qubits. At the same time, researchers develop improved algorithms and error correction methods designed to harness the power of quantum computation. Even if fully scalable quantum computers remain some distance in the future, the effort to build them has already sparked the growth of a broader scientific discipline known as quantum information science. This expanding field explores how information behaves when encoded within quantum systems. It connects ideas from physics, mathematics, computer science, and engineering into a rapidly evolving area of research. One particularly exciting direction within this field involves new forms of communication that rely on the unique properties of quantum mechanics. As quantum information science has developed, researchers have discovered that the strange rules of quantum mechanics can be used not only for computation but also for communication. In particular, the unusual relationship between measurement and quantum states allows information to be shared in ways that can be fundamentally secure. This idea forms the foundation of quantum cryptography. Cryptography is the science of protecting information so that only intended recipients can read it. Modern digital communication relies heavily on cryptographic systems to secure messages, financial transactions, and private data moving across the internet. Most of these systems depend on mathematical problems that are extremely difficult for classical computers to solve. For example, many encryption methods rely on the difficulty of factoring very large numbers. However, as discussed earlier, sufficiently powerful quantum computers could eventually weaken some of these traditional cryptographic techniques. This possibility has encouraged scientists to develop entirely new forms of encryption based directly on the laws of physics. Quantum cryptography takes advantage of the fact that measuring a quantum system inevitably changes its state. One of the most widely studied methods in this field is known as quantum key distribution. In quantum key distribution, two parties exchange a secret cryptographic key using individual quantum particles, often photons. These photons are prepared in carefully chosen quantum states that encode information. Because quantum states cannot be measured without disturbing them, Any attempt by an eavesdropper to intercept the particles will introduce detectable changes. The legitimate users can compare a portion of their data to check for these disturbances. If the transmission shows signs of interference, they know that the communication may have been compromised and can discard the key. If no interference is detected, the key can be used to encrypt messages with a high level of security. This method does not rely on the computational difficulty of solving a mathematical puzzle. Instead, it relies on fundamental principles of quantum measurement. One of the earliest and most influential quantum key distribution protocols was developed in the early 1980s by Charles Bennett and Gilles Brassard. Their approach demonstrated how single photons could be used to establish secure cryptographic keys between distant locations. Since that time, laboratories around the world have tested and improved these techniques. In recent years, quantum communication experiments have expanded beyond small laboratory setups into large-scale demonstrations involving long-distance transmission. One of the most striking examples involves satellite-based quantum communication. In 2016, the Chinese Academy of Sciences launched a satellite known as Mihyas, named after an ancient Chinese philosopher. This satellite was designed specifically to test quantum communication technologies in space. The Mihyas satellite carried equipment capable of generating entangled photon pairs and transmitting them to ground stations separated by thousands of kilometers. These experiments demonstrated that quantum key distribution could operate over distances far greater than those achievable using optical fibers alone. Researchers used the satellite to establish secure communication links between ground stations in different regions of China, and even conducted quantum encrypted video calls between distant cities. These achievements represented an important step toward the development of global quantum communication networks. International collaborations have also played a major role in advancing this field. Scientists from universities and research laboratories across Europe, North America, and Asia continue to investigate new methods for transmitting quantum information across longer distances with greater reliability. Many of these efforts focus on the concept of a quantum network. A quantum network would connect quantum devices across large distances using channels capable of transmitting quantum states. Such a network could link quantum computers, sensors, and communication systems into a larger infrastructure sometimes described as a quantum internet. In such a system, entangled particles could be distributed between distant nodes. This shared entanglement could enable new forms of communication and coordination that have no direct counterpart in classical networks. Developing these networks requires overcoming significant technical challenges. Quantum states are extremely fragile and can easily be disrupted by interactions with the surrounding environment. Even small losses in optical fibers or tiny disturbances in experimental equipment can destroy the quantum properties needed for communication. To address this problem, scientists are developing devices known as quantum repeaters. Quantum repeaters are designed to extend the range of quantum communication by carefully storing and retransmitting quantum states while preserving their coherence. Building reliable repeaters remains an active area of research involving many laboratories around the world. Despite these challenges, progress continues steadily. Experimental demonstrations of quantum communication now span hundreds and even thousands of kilometers. Researchers have also achieved secure quantum key distribution through urban fiber networks connecting multiple cities. These experiments suggest that quantum communication systems may eventually become part of the global communication infrastructure. The long-term vision involves networks capable of transmitting quantum information alongside classical data, enabling secure communication channels and new scientific applications. While these technologies continue to develop, they also highlight something deeper about the nature of quantum physics itself. The same principles that once puzzled early physicists studying atoms and light now provide tools for building entirely new kinds of technology. At the same time, quantum mechanics continues to raise profound questions about the nature of reality, observation, and information. Stepping back from the technical details reveals that quantum physics has not only reshaped scientific understanding and technological capability, it has also changed how scientists think about the fundamental structure of the universe itself. By the time scientists had developed the mathematical machinery of quantum mechanics, they possessed a theory capable of predicting the behavior of atoms, electrons, and photons with extraordinary accuracy. Experiments repeatedly confirmed its predictions. Technologies built upon it reshaped modern society. Yet a curious situation remained. Physicists agreed almost completely on how to use the equations of quantum theory, but they often disagreed about what those equations actually meant. This situation gave rise to one of the most fascinating intellectual debates in the history of science. The discussion concerns the interpretation of quantum mechanics, meaning the deeper explanation of what the theory says about reality itself. The most historically influential interpretation is known as the Copenhagen interpretation. This view was developed during the 1920s by physicists including Niels Bohr and Werner Heisenberg, working closely with colleagues at the University of Copenhagen. According to the Copenhagen interpretation, the wave function provides a complete description of a quantum system. The wave function contains information about all possible outcomes of a measurement expressed as probabilities. Before a measurement takes place, a system exists in a superposition of possibilities. When a measurement occurs, the wave function collapses, producing a definite outcome. In this view, quantum mechanics does not describe a particle having a precise position and motion in the classical sense. Instead, it describes probabilities for different results that might be observed. Niels Bohr emphasized that classical concepts such as position and momentum can only be defined through the act of measurement. According to Bohr, the experimental setup used by an observer plays an essential role in determining how a quantum system is described. This interpretation proved enormously practical for working physicists. It allowed scientists to calculate experimental outcomes successfully without needing to specify an underlying picture of microscopic reality. However, not everyone felt comfortable with the idea that measurement might play such a fundamental role. Albert Einstein was one of the most famous critics of the Copenhagen interpretation. Einstein believed that a complete theory of nature should describe physical reality independently of observation. His concerns led to the Einstein-Podolsky-Rosen argument proposed in 1935, which questioned whether quantum mechanics provided a complete description of reality, although later experiments showed that quantum predictions remain correct. Einstein's challenge sparked decades of debate about how the theory should be interpreted. One alternative interpretation emerged during the 1950s through the work of the American physicist Hugh Everett. Everett proposed what is now known as the many worlds interpretation. According to this idea, the wave function never collapses. Instead, every possible outcome described by quantum mechanics actually occurs, each within its own branch of a continually expanding universe. In this picture, the universe constantly splits into multiple histories whenever a quantum event with multiple possible outcomes takes place. For example, if a quantum measurement could produce two possible results, the many worlds interpretation suggests that both outcomes occur, each in a different branch of reality. Observers within each branch experience only one result, giving the impression that the wave function has collapsed. Although this idea may sound like science fiction, it follows naturally from the mathematical structure of quantum theory if the collapse of the wave function is removed from the equations. The many worlds interpretation has been studied by physicists and philosophers for decades. Some researchers find it appealing because it avoids introducing special rules for measurement. Others feel uneasy about the existence of countless parallel branches of reality. Another perspective takes a different approach. Pilot wave theory, associated with the physicist David Bohm, attempts to restore a more classical picture of particles moving along definite trajectories. In Bohmian mechanics, particles always possess precise positions and motions. However, their behavior is guided by a mathematical entity known as the pilot wave. The pilot wave evolves according to the same wave equation used in standard quantum mechanics. It influences the motion of particles in a way that reproduces the statistical predictions of quantum experiments. This interpretation preserves determinism, meaning that the future behavior of a system is determined by its current state. Yet it introduces a non-local guiding wave that can influence particles across distance. Because of this non-local feature, Bohmian mechanics predicts correlations similar to those observed in experiments involving quantum entanglement. Although pilot wave theory remains less widely used than other interpretations, it continues to be studied as an alternative way of understanding quantum phenomena. These competing interpretations highlight a remarkable aspect of quantum mechanics. The mathematical structure of the theory remains the same regardless of which interpretation one adopts. Experiments consistently confirm the predictions of quantum mechanics, yet the underlying explanation of what is happening remains open to discussion. Philosophers of science have also contributed to this conversation. Researchers studying the foundations of physics examine questions about probability, measurement, and the relationship between physical theories and reality itself. Institutions such as the Perimeter Institute for Theoretical Physics and the University of Oxford host research programs devoted to these foundational issues. These discussions do not suggest that quantum mechanics is uncertain or unreliable. On the contrary, it is one of the most precisely tested theories in the history of science. Quantum electrodynamics, the quantum theory describing the interaction of light and charged particles, produces predictions that match experiments to extraordinary precision. Some measurements agree with theoretical calculations to more than 10 decimal places. What remains uncertain is not the accuracy of the theory, but the deeper interpretation of what the equations reveal about the nature of reality. Quantum physics challenges many assumptions that arise from everyday experience. In the macroscopic world, objects appear to possess definite properties at all times. A ball rests on a table at a specific location. A planet follows a predictable orbit around a star. At quantum scales, the situation becomes more subtle. Particles may exist in superpositions of possibilities. Entangled systems display correlations that span large distances. Measurements influence the outcomes that observers ultimately record. These features may feel counterintuitive, yet they are supported by an immense body of experimental evidence. Over time, physicists have learned to accept that the microscopic world operates according to principles very different from those governing everyday experience. The success of quantum mechanics suggests that nature does not always conform to human intuition. Instead, it invites scientists to expand their understanding of reality, guided by careful observation, precise mathematics, and an openness to ideas that once seemed impossible. Seen in this light, quantum physics becomes more than a collection of equations. It becomes a window into the deep structure of the universe itself, hinting that the nature of reality may be richer and more subtle than classical physics ever imagined. Reflecting on these ideas naturally leads to a broader perspective on the quantum universe and humanity's continuing effort to understand it. The story of quantum physics is, in many ways, a story about how humanity gradually learned that the universe is stranger than it first appears. For centuries, scientists believed that the laws governing nature were largely understood. Classical physics, shaped by Isaac Newton in the 17th century and expanded by James Clerk Maxwell in the 19th century, seemed capable of explaining almost everything. Planets followed predictable paths. Light behaved like waves travelling through space. Matter appeared solid, stable, and well-behaved. Then, near the end of the 19th century, a few stubborn puzzles began to appear. These puzzles seemed small at first. They involved the colours emitted by heated objects, the structure of atoms, and the way light interacted with metal surfaces. Yet these small inconsistencies quietly revealed that the classical picture of nature was incomplete. When Max Planck introduced the idea that energy could be emitted in discrete packets in the year 1900, he was attempting to solve a specific problem involving thermal radiation. Few people at the time realized that this modest proposal would eventually transform the foundations of physics. Albert Einstein soon extended the idea further in 1905 by showing that light itself could behave as particles known as photons. His explanation of the photoelectric effect demonstrated that energy and frequency were intimately connected in the behavior of light. Not long afterward, Niels Bohr proposed a new model of the atom in which electrons could occupy only certain allowed energy levels. Werner Heisenberg introduced a new mathematical framework describing quantum systems in terms of observable quantities. Erwin Schrödinger developed a wave equation that allowed physicists to calculate how quantum systems evolve over time. Together, these scientists and many others created the foundation of quantum mechanics during the early decades of the 20th century. Their discoveries revealed a microscopic world governed by rules very different from those of classical physics. Particles could behave like waves. Energy appeared in discrete quantities. The exact position and motion of a particle could not both be known with perfect precision due to the uncertainty principle formulated by Werner Heisenberg. Instead of describing nature with perfectly predictable trajectories, quantum theory described probabilities and possibilities. At first, these ideas felt deeply counterintuitive. Even the scientists who developed the theory struggled to reconcile its implications with everyday experience. Yet experiment after experiment confirmed that quantum mechanics worked. The theory accurately described the spectra of atoms, the behavior of electrons in solids, the interaction between light and matter, and countless other phenomena. Over time, it became clear that quantum physics was not merely a mathematical curiosity. It was a fundamental description of how the universe operates at its smallest scales. The strange principles discovered by Planck, Einstein, Bohr, Heisenberg, Schrödinger, and their colleagues now form the backbone of modern physics. Every atom, every molecule, and every piece of matter follows these quantum rules. The stability of atoms arises from quantum energy levels. Chemical reactions depend on the arrangement of electron orbitals. The colors of materials reflect quantum transitions between energy states. Even the existence of solid matter depends on the Pauli exclusion principle, discovered by Wolfgang Pauli, which prevents electrons from occupying identical quantum states within an atom. Without that principle, the structure of matter would collapse in ways that make the familiar world impossible. In this sense, the entire physical universe rests upon quantum foundations. At the same time, quantum physics quietly powers much of modern technology. The transistors inside computers and smartphones rely on the quantum behavior of electrons within semiconductor materials. Lasers, first proposed through Albert Einstein's work on stimulated emission, enable high-speed communication through fiber optic networks. Magnetic resonance imaging scanners allow doctors to observe the internal structure of the human body by manipulating the quantum properties of atomic nuclei. Emerging technologies such as quantum computing and quantum communication continue to push these ideas into new frontiers. Yet despite all of this progress, quantum physics still contains unanswered questions. Scientists continue investigating the nature of quantum measurement, the interpretation of the wave function, and the possibility of unifying quantum mechanics with gravity. The search for a theory of quantum gravity remains one of the great challenges in theoretical physics. Researchers studying black holes, the early universe, and the structure of space-time continue exploring how quantum principles might apply to gravity itself. Experimental physicists are also probing quantum phenomena with increasing precision. Particle accelerators such as the Large Hadron Collider at CERN explore the smallest known building blocks of matter. Laboratories around the world develop increasingly sophisticated experiments designed to test quantum effects in larger and more complex systems. Some experiments now demonstrate quantum behavior in objects containing thousands or even millions of atoms. These efforts gradually blur the boundary between the microscopic quantum world and the familiar macroscopic world of everyday life. Looking back over the past century, it becomes clear that quantum physics has profoundly reshaped humanity's understanding of nature. The universe once appeared to be a predictable machine governed by straightforward mechanical laws. Quantum mechanics revealed that reality contains layers of complexity far beyond that simple picture. At the smallest scales, nature operates through probabilities, superpositions, and subtle correlations that span distance and time. Yet these strange behaviors do not make the universe chaotic or unknowable. Instead, they reveal a deeper structure governed by precise mathematical relationships and consistent physical laws. For many scientists, this realization inspires a sense of quiet wonder. Every object, every living organism, and every star ultimately arises from the interactions of atoms obeying quantum rules. Beneath the familiar world of everyday experience lies a vast microscopic landscape of particles, waves, and fields constantly interacting in subtle ways. Most of these processes unfold far beyond human perception. Electrons move through atoms, photons travel across space, and quantum fields fluctuate silently throughout the universe. The fabric of reality hums with activity at scales far smaller than anything the human eye can see. Yet those hidden processes give rise to everything that exists. Recognizing this connection can change the way one looks at the world. A grain of sand, a leaf on a tree, or a beam of sunlight all represent the outcome of countless quantum interactions unfolding continuously beneath the surface of reality. Understanding quantum physics does not remove the mystery of the universe. If anything, it deepens that mystery while revealing the astonishing consistency of the laws that govern nature. Seen from this perspective, the quantum world is not distant or abstract. It is the quiet foundation upon which every moment of existence unfolds. Reflecting on that idea naturally leads to a final thought about the remarkable journey that quantum physics has taken over the past century and the discoveries that may still lie ahead. The journey through quantum physics begins with the simple realization: the universe behaves very differently when observed at extremely small scales. Early scientists studying atoms and light discovered patterns that classical physics could not explain. From these puzzles emerged new ideas about energy, matter, and probability. Max Planck introduced the concept of energy quanta. Albert Einstein revealed that light could behave like particles called photons. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger helped construct the mathematical framework that now describes the quantum world. Over time, these discoveries revealed a universe governed not by perfectly predictable trajectories, but by probabilities and possibilities. Particles can behave like waves. Electrons occupy probability clouds rather than fixed orbits. Quantum systems can exist in superpositions, holding multiple potential outcomes at once until measurement reveals a specific result. Even more remarkably, particles can become entangled, forming connections that link their properties across distance in ways that once seemed impossible. These ideas may sound strange, yet they form one of the most successful scientific theories ever created. Quantum mechanics predicts experimental results with astonishing accuracy, and the technologies built upon it quietly shape modern life. Every transistor inside a computer chip, every laser beam used in communication, and every magnetic resonance imaging scan performed in hospitals relies on the quantum behavior of matter. Even the stability of atoms themselves depends on the rules discovered during the early days of quantum theory. This means that the calm surroundings of everyday life are quietly governed by the activity of particles and fields operating at scales far too small to see. Beneath the surface of the visible world lies a microscopic universe, filled with electrons, photons, and quantum fields constantly interacting. Understanding these processes does not make reality feel less mysterious. Instead, it reveals that the universe possesses a deep and elegant structure, even when that structure challenges ordinary intuition. By exploring the smallest parts of nature, quantum physics invites a new perspective on reality itself. It suggests that the familiar world emerges from countless interactions unfolding far below the limits of human perception, reminding us that even the quietest moments are built upon an extraordinary and intricate foundation.